Sometimes the simplest solution may be the optimal one. Hello, everyone. Today I want to share a particularly interesting research finding with you. In a recent study published by research teams, including Meta, they discovered a surprising phenomenon. In the transformer architecture, the normalization layer, which was considered indispensable, can actually be replaced by a mathematical formula so simple it's almost unbelievable. dyT x equals tan alpha x. That's right, it's that simple. This discovery comes from a paper titled Transformers Without Normalization. This discovery not only challenges traditional perceptions in deep learning, but also provides a whole new perspective for model design. Before diving in, let's first review some background knowledge. Over the past decade, normalization layers have been regarded as one of the fundamental components of modern neural networks. Starting with the introduction of batch normalization, BN, in 2015, to the later layer normalization, LN. These techniques have become the must-have tools in the deep learning community, helping us train deeper and larger models, accelerate convergence, and improve model performance. At this point, some friends might ask, why is normalization so important? Let me explain with an example from daily life. Imagine if we want to compare the exam scores of students from different classes. Directly comparing the raw scores may not be fair because the difficulty of the exam papers and the grading standards are not the same for each class. At this time, we usually convert the scores into standard scores or rankings so that we can make a more reasonable comparison. In deep neural networks, normalization layers are like such a standardization tool. When data flows through the network, the activation values of different layers may vary significantly. Some are particularly large, some are particularly small, like different standardized test scores. This imbalance can lead to unstable training, and the normalization layer is responsible for pulling these values back into a reasonable range. Especially in deep networks like transformers, the importance of layer normalization is self-evident. It acts like a balancer in the network, ensuring that information does not deviate during transmission. This is why, over the past decade, normalization has been considered an indispensable component in deep learning. So how does DYT, dynamic hyperbolic tangent, manage to replace this magic tool? The analysis by the research team is particularly interesting. They found that in transformers, layer normalization actually produces a special pattern of data transformation, a curve resembling an S shape. This discovery can be said to have opened the door to a new world. This pattern mainly has two functions. 1. Properly scaling the input. 2. Compressing extreme values into a reasonable range. Let's understand through a concrete example. Suppose when processing a piece of text, some words may produce particularly large activation values, such as 10 or greater, while the activation values of other words may be close to 0. Traditional layer normalization standardizes these values by calculating the mean and variance. And DIT is like a smart imitator, which replicates these two key functions in the simplest way. First, tan function itself is an elegant S-shaped curve, naturally capable of compressing extreme values, that is, compressing all values between -1 and 1. And the learnable parameter alpha is like a tuner, responsible for finding the most suitable scaling ratio. At this point, you might think, is this too simple? That's right. What's even more surprising is that this replacement, most cases, does not even require adjusting the original training hyperparameters. The research team found that as long as the initial value of alpha is set to 0.5, it can achieve good results in most tasks. Of course, this method is not perfect. In traditional CNNs, convolutional neural networks, such as the old-timer models like ResNet and VGG, replacing batch normalization with DYT results in a certain performance drop. This result also reminds us that in practical applications, we should choose the appropriate technical solution based on the specific scenario. This research tells us a very interesting truth. Sometimes the simplest solution might be the best in the rapidly developing field of deep learning. Shouldn't we also stop from time to time and rethink those assumptions that are considered taken for granted? All right, that's all for today's sharing. If you're interested in this research, feel free to leave a comment and discuss in the comment section.